Section 8.8, Improper Integrals. We have two objectives for this lesson. One, you will know the different types of improper integrals. And two, for each type of improper integral, you'll be able to determine whether the improper integral converges or diverges. Before we start talking about improper integrals, we've learned about two other types of integrals in calculus: indefinite integrals and definite integrals. So if you have an indefinite integral, there are no limits of integration. And what you're looking for is a family of antiderivatives for the integrand. If you have a definite integral, you have limits of integration. And you evaluate a definite integral by using something called the fundamental theorem of calculus. And the definite integral would be a number, and it would represent the area of the region between the graph of the integrand and the x-axis between x is equal to 1 and x is equal to 2. So what makes an integral improper? Let's think about what makes a definite integral. So to understand what an improper integral is, let's first go back and review what a definite integral is. So here we have the definition of a definite integral, and it says you have a function defined on a closed interval from a to b, and the limit that you have here, which is the limit of a Riemann sum as the norm of the partition approaches 0. If that limit exists, then we say the function f is integrable on the closed interval from a to b, and the limit of this Riemann sum as the norm of the partition approaches 0 by definition gives us a definite integral. So to note is that we have the definition of a definite integral defined where the interval from a to b is a closed interval. So that's one way in which you can have something that doesn't fit this definition. What if you don't have a closed interval, such as we have here? The upper limit of integration is infinity, so the interval that we have is from 1 to infinity, which is not a closed interval. So that's one way in which you can have an improper integral. Let's look at another way in which we can have an improper integral. And to understand why, we're going to look at what we use to evaluate definite integrals, which is the fundamental theorem of calculus. This is the definition of a definite integral, but to actually evaluate a definite integral, we've been using the fundamental theorem of calculus. So let's take a look at that to understand how we can have the second type of improper integral. So here we have the fundamental theorem of calculus, and that's what we've been using to evaluate definite integrals. And it says if a function f is continuous on the closed interval from a to b, and uppercase f is an antiderivative of the integrand on the closed interval from a to b, then the definite integral of f of x dx from a to b is equal to the antiderivative of the integrand evaluated at the upper and lower limits of integration and then subtracting. So the key thing that I want to focus on to help you understand the second type of improper integral that we can have is the requirement that the integrand be continuous on the closed interval from a to b. So when you look at what you have here, you might at first glance think that it's a definite integral, because unlike the first type of improper integral where obviously one of the limits of integration is infinity, here both limits of integration are numbers. So you do have a closed interval from 0 to 1 in my example here. However, this is an improper integral because of the requirement from the fundamental theorem that the integrand be continuous on the closed interval. So here the integrand is 1 over x squared, and it is going to have an infinite discontinuity at x is equal to 0. Because what happens as x approaches 0 from the right side of 0, this is our interval, so we're only approaching 0 from the right side of 0. What happens is that the denominator will get really small, and when you divide 1 by really small positive numbers, the quotient will approach infinity. So we have an infinite discontinuity, so our function is not continuous on the closed interval from a to b, and therefore this is not a definite integral. It's an improper integral for that reason. So we just looked at an improper integral that has an infinite limit of integration and an improper integral that has an infinite discontinuity. Those are the two main types of improper integrals. Let's take a look at how we define each one. So these are the two main classes of improper integrals. So in the first class, we have infinite integration limits. So as I said earlier, we've actually been working with this before when we were learning about the integral test. Maybe I didn't say that, but we did work with this before when we were learning about the integral test, when we were learning about infinite series. So you've seen this before, but this is one of 3 possible variations that you can have for the first class of improper integral. So they're all having to do with the fact that either one or both of the limits of integration are infinite. And if one of them is infinite, it could be the upper limit of integration or the lower limit of integration. So what does it mean to have this improper integral? You can interpret it still in terms of area. You're basically asking this question. If we had a definite integral, we know that we would interpret this as area between the graph of f and the x-axis from a to whatever the upper limit of integration is. So when we have an improper integral, we can still think in those terms, but now we're thinking, okay, we have the graph of the integrand, we have the horizontal axis, and we have the interval from a to infinity. So this shading that I'm doing in green, it would just keep going forever. And the question is, what is the area of this seemingly infinite region? Does it actually have a finite area, or does it have an infinite area? So you can think in those terms. And if it turns out that the area of this region where the graph of f keeps going without end, if it turns out to have a finite area, we say the improper integral converges. If it turns out to have an infinite area, we say the improper integral diverges. So based on that idea, we have the definitions that we'll look at here. So let's look at this definition. So if you have an improper integral where the upper limit of integration is infinity, again, you've seen this before when we were learning about the integral test. What you do is you are going to turn it into something that you know how to work with, which is, of course, a definite integral. You know how to work with that using the fundamental theorem of calculus. So change the upper limit of integration into b, which is a variable, and we're going to take the limit of this definite integral as the variable b, which would represent some numerical value, as that b value goes to infinity. So that's basically taking something that we're thinking about now and rewriting it in terms of something that we've already worked with before. So we know how to work with this because we're treating b as a constant. So we use the fundamental theorem of calculus, and then we take the limit of that definite integral as the upper limit of integration b goes to infinity. So we're taking two concepts that we've learned about before, definite integrals and limits, and putting them together to define what an improper integral of this class would be. And if you look at the other definitions for the other cases, they're basically the same idea. The only thing that we have to take note of is that in the second variation, it is the lower limit of integration that is negative infinity. So still you do the same thing. You write a definite integral where the lower limit of integration is now represented by a, and you take the limit of that definite integral as a approaches negative infinity. And in the third case, you basically have a combination of the first two cases, where you have the lower limit of integration is negative infinity, the upper limit of integration is positive infinity. So how do you work with that? You basically put what we just did in cases 1 and 2 together. So the idea is this. You've got the interval from negative infinity to infinity, and if you choose some number, whatever that number may be, here represented by the generic c, you can divide the interval from negative infinity to positive infinity as from negative infinity to c, union from c to infinity. Of course, if I wanted to be technical here, I would make one of these technically correct. I would make one of these closed to include c. But that's what we have. So we're taking the case that we have in 3 and rewriting the improper integral as a sum of two improper integrals. And for each one of these, we looked at how to deal with them in cases 1 and 2. Now let's consider the second class of improper integrals where you have a value between your limits of integration at which the integrand has an infinite discontinuity. And you could have more than one infinite discontinuity on the given interval, a finite number of infinite discontinuities. So this is an example that fits the second category. Now, at first glance, you might think it's a definite integral, but it's an improper integral because if you look at the integrand, at x is equal to 0, which is the lower limit of integration, you have an infinite discontinuity. So how do you deal with it if you have a problem like this? Let's look at these definitions here. Well, before I look at the definition formally, let's look at the example that we have. The problem that we have is at 0. The problem that we have is that at x is equal to 0, the integrand has an infinite discontinuity. So the way we can deal with it is as follows. The integrand has a discontinuity at 0, but we would have no problem if we considered the open interval from 0 to 1. But of course, we can't do that with the fundamental theorem of calculus. So here's the adjustment that we're going to make. We're going to say, let's go ahead and write a variable here, c. And we're going to make c be coming from here. So not including 0. Not including 0, so we would have no problem with the discontinuity. So we're going to write from c to the upper limit of integration, 1, of 1 over x squared dx. Again, the problem is at x is equal to 0. So we're not going to consider c to be 0. Let's not think about what happens when c is 0. So c is going to be greater than 0. As long as c is greater than 0, we have no problem. We're okay. But c has to be greater than 0. So because if c were 0, we would have an infinite discontinuity, and the fundamental theorem of calculus would not be applicable. So let's make sure that c is not 0, but c can be any number that's greater than 0. So what we do is we write, we have this definite integral from c to 1, but we want to make sure that c is greater than 0 so that we won't have that problem. So we just say let c approach 0 from the right side. So c is never equal to 0, but always greater than 0. So that's what we have going on in case number 2. And case number 1 is similar. The only thing is you have it so that the problem is at the upper limit of integration. So you let the upper limit of integration be c, and you let c approach the value at which you had the infinite discontinuity from the left side. And case 3 is a combination of the first two cases, where you have an infinite discontinuity somewhere between a and b. And the way you take care of that is you say, okay, at what value of x do I have that infinite discontinuity? Let's say at x is equal to c. So let's go ahead and write our definite integral as a sum of two definite integrals. So now we would deal with each one like we did in case 1 and case 2. So let's look at some examples to make this concrete. So here we have example 1, an improper integral of the first type, where the upper limit of integration is infinity. So we're going to have to use this definition and rewrite that as the limit. So we have the definite integral here, so where we replace infinity with b, and we take the limit of this definite integral as b approaches infinity. And we're going to evaluate this limit, and here's the key part. If this limit exists, we say the improper integral converges. If this limit does not exist, we say the improper integral diverges. That's what you have to do. So for this example, the integrand is 1 over x. So the antiderivative will be natural log of x. And then using the fundamental theorem of calculus, because that's what we have here, a definite integral, so you can use the fundamental theorem of calculus, evaluate the antiderivative at the upper and lower limits of integration, and take the limit of that. So you're going to evaluate the antiderivative at the upper and lower limits of integration and subtract, and take the limit of this quantity as b approaches infinity. And when you do that, you will have the limit of natural log of b as b approaches infinity, which is infinity. So it's not a number, the limit does not exist, the improper integral diverges. So here we have two examples where the improper integral converges. So again, it's improper integrals of the first type, where one of the limits of integration is infinity. In both cases, the upper limit of integration is infinity. So we're going to begin by rewriting each definite integral as the limit. We're going to begin by rewriting each improper integral as the limit of a definite integral as b approaches infinity, where b is the upper limit of integration. So that's what we're doing here for each of them. Again, you rewrite this so that the upper limit of integration becomes b. So your improper integral is rewritten as the limit as b approaches infinity of a definite integral. And you're going to evaluate the definite integral using the fundamental theorem of calculus. So that's what we're doing here. And then you take the limit of the result as b approaches infinity. So when you do that, you get a number here. You get a number here as well. So the limit exists and the improper integral converges. You're using the arctangent rule to find the antiderivative here. So in example 4, you have an improper integral of the third type. And the way you deal with that is, let's go ahead and divide the infinite interval into two subintervals, one from negative infinity to 0 and one from 0 to infinity. And you're going to take a look at each one of these using the first two definitions, just like we saw for our first two examples. And when you do that, again, you need to find an antiderivative of the integrand using techniques that we've learned before. And when you do that, you get your antiderivative, use the fundamental theorem of calculus. Of course, again, you have to first rewrite your limits of integration as b, and you're taking the limit of this definite integral as b approaches negative infinity here, and you're taking the limit of this definite integral as b approaches positive infinity here. But both of these improper integrals converge, and because both of them converge, we say the improper integral here converges. If one of them had diverged, we would say the improper integral diverges. So now we look at an example of the second type of improper integral that we can have, where we have an infinite discontinuity somewhere within the interval of integration. So what you see here is you have an infinite discontinuity at x is equal to 0, because when x is equal to 0, the integrand would be approaching infinity. So what you need to do is you have to use this definition . So what we have is the second case here, and what you can do is you can replace the lower limit of integration with c and take the limit of this definite integral as c approaches 0 from the right. Now, why do we do this? Because the discontinuity is at x is equal to 0. So as long as x is not equal to 0, we don't have a problem. So we just write this as a definite integral, and we take the limit of that as c approaches 0 from the right. So we don't have a problem. And then you can evaluate this definite integral using the fundamental theorem of calculus. Once you get your answer, take the limit as b approaches 0 from the right. You get a limit, so the limit exists, and if the limit exists, we say the improper integral converges. Let's take a look at example 8. This is a situation like we have for number 3 here, where you have an integral. It's an improper integral. The limits of integration are from -1 to +2. The problem happens somewhere in between -1 and +2. It happens at x is equal to 0, because our integrand will have an infinite discontinuity when x is equal to 0. So the way you deal with that is you write this as the improper integral from -1 to 0 plus the improper integral from 0 to 2. And once you've done that, you're going to deal with each one of these using the definitions from 1 and 2 before. So in the first case, the problem is happening at x is equal to 0. So you're going to rewrite that as the limit of the definite integral from -1 to c of 1 over x cubed dx as c approaches 0 from the left of 0, plus this one here, you're going to rewrite that as the limit of the definite integral from c to 2 of 1 over x cubed dx as c approaches 0 from the right side of 0. And then you would have to evaluate each of these definite integrals using the fundamental theorem of calculus, and then whatever answer you get, take the limit as c approaches 0 from the left here and as c approaches 0 from the right. If one of them diverges, the improper integral would diverge. For the improper integral to converge, both of these would have to converge. And in this case, this one diverges, and because of that, the improper integral that we have for the problem would also diverge.